What is going on, guys, and welcome back to another one of the videos. As I said, I'm recording this right after the statement video, where basically the information for my channel is going to be shared. That doesn't matter. Today we have the first scientific analysis, I should say, explanation, maybe, right, to put this a little bit better. So let's have a look. What are we gonna be diving into today? We have forces and torque. This is what we're going to be looking at today, and well, let's start from the beginning, right, as we always do. Let's assume that you guys and I also have no knowledge of any of this, right? What is a force? What is a torque, right? So imagine a system of coordinates, right? So we have x, y. Let's just say it's two-dimensional, right? So we have x here and we have y here, right? Good. And now what I'm gonna do is I'm gonna actually draw any line here, right? Any line. It has some kind of function, right? But that is not relevant to us right now, right? So what I'm gonna do is draw this thicker for you guys. And this is actually gonna be our line along which our vector or our force is gonna basically be, right? So when we have vectors or forces, our vector or force that we're gonna be looking at is gonna be just like this, right? So let's just say that my vector is here, right? Is this long, and it's this long, right? Let's just call this length L, right? This is the length of my vector. So important thing to know is that if my vector is here, this same vector can also be here, right? And be anywhere, but it must share the same direction, share the same length, and share the same line on which it is on, right? So maybe a way to imagine this is, say you're outside, you're pushing your little brother or sister on their bike, right? Or on their whatever, like four-wheeler, you know what I mean? Something like that you can actually push, right? So think that it does not really matter whether or not you're actually pushing this thing, this cart, right? So the cart would be here, then we would have two wheels right here, and then think it doesn't really matter whether or not, or whether you're pushing the cart from this side or whether you're pulling the cart from this side, right? These two forces are the same, they're looking in the same direction, and they are equally large. That is the reason that it doesn't matter whether or not I draw the force here or here. What I must not do is draw it in the way that I actually drew it here, right? This is just to visualize. If I actually am pulling only here or here, then of course the other force goes away. What I can do though is this, or I flip it around. I erase this and I put the other force there, right? So let's just assume that I'm pushing it, right? Push. Good. So I hope you guys understood that, right? This is the basic principle on which this is gonna work. So, okay, now that we have basic understanding of what a force is, let's have a look at what a force even is, right? So we just said it's an arrow, it's, I don't know, it's something, right? Well, Newton actually discovered this, right? And the reason that I say that Newton discovered this, right, is because force is mass times acceleration. This is a formula that most of you guys most likely know, right? F is m times a. And so why do I say that Newton actually discovered this? Well, if you look at the units, right? The unit is actually Newton, right? So you have the unit Newton is equal to kilograms times acceleration. What is the unit there? Of course, meters per second squared, right? So this is actually the unit of Newton, right? 1 Newton is, and this is important to know, right? If you have Newton is equal to kilograms times meters per second squared, right? This is the same as this, right? These two are the same as this. Important to know, you know, not really like groundbreaking idea, but it is important to remember that because these two multiplied by each other equal to Newton, you don't need to write Newton, you can also write this, right? This is the unit of the force. So I think we all know what a mass is, right? Mass is just the weight of some object on our Earth here, and sorry about that. Mass is the weight regardless of where you are. That's correct. And then acceleration is of course the Earth's gravity field, which is defined, or at least we here in Europe calculate with A is equal to 9.81, right? And if I write A, then I should actually write G, because this is how it is defined, right? So G is equal to 9.81 here in Europe. Good. So we've now clarified what a force is. So what does this do for us now? How does this help us? Okay, let's just have a look. So let's just say, right, that you're sitting on a bench. So you have your bench here and you're sitting on it somewhere, right? Let's just say that these are the feet from the bench. All right, and you're sitting, let's just say that you're a greedy kid and you're sitting right in the middle. Okay, so you're sitting right in here. What does this actually mean? Well, this is actually the basic principle from which everything on this world is calculated. Forces and the resulting moments and everything else, right? So you have a force here, F here. Now the question would be, how big are these two forces? Because one thing that I also want to teach you guys in this video is that if a force has no counterpart, something has to be moving. The sum of all forces has to be zero. So this is something very important, right? So we have sum. This is the sign for sum of all forces in any direction. So if I write a y here, it's in the y direction, right? If we define our system of coordinates like this, x, y. If we define positive y in this direction, positive x in this direction, then we have the sum of all forces in y direction is equal to, what is it actually equal to? Well, of course, you have F, but okay, well, we said previously that this is the positive F direction, right? So what is the positive direction in general, right? What happens if this force is actually flipped? Well, negative, right? I mean, if you're going into the positive direction, you turn around by 180 degrees. We all know that you're going into the negative direction. So that's actually what's happening here, right? So we are actually flipping this force, and we're actually saying, okay, negative F, because it's looking down, right? And now comes the interesting part, because you're sitting exactly in the middle, right? Some of you guys might say, okay, right, this is just a length over 2, right? And this is the whole length. Let me just actually define that straight away. Let's not mess around with this. Length over 2, whole length. So some of you guys might say, okay, we are gonna need a force here that is equally large to this force, and another one here that is equally large to this force to compensate this. But that's actually incorrect, because if you have a look at this, right, I said that the sum of all forces must be 0. So if you had minus F plus F plus F, that would be plus F, which is not equal to 0, right? Assuming that F is not equal to 0, of course. So you actually have to have F over 2, and I will explain why in a second. So we have now established that you have two forces looking up, one force is looking down, one force is F, and the other two forces are F over 2. Well, why is that? Because we are also talking about torque today, and torque is another thing that is very important for today, right? So instead of just saying, okay, what is the sum of all forces, you can also say, what is the sum of all torques, right? So sum of M, and then you do this straight line down, and that basically just means around which point, because okay, let's define a moment, of course. So let's do that first, right? So what is a torque? So M stands for torque is equal to what? Let's maybe write down the units, right? So Newton meter, right? What does this mean, Newton meter? Well, Newton meter is the same as having Newton times meter, right? And that actually already hints towards what this actually is, right? So you have M has to be F, right? It has to be F because the unit of F is Newton, right? And then times M, what has the unit M, meter, right? This is just any unit or measurement of length, right? So you have M here in meters, and you have N here in Newton. Newton meter, Newton times meter. And how can you guys think of this, right, as this torque, right? So, well, one way to think about this is you're actually, let's say you have to unscrew something, right? And you're unscrewing, but you're trying too hard. I mean, you're trying hard, but you can't get the screw to actually unscrew, right? So the question is, why is that? Well, if we look at the formula, right? M is F times L. When we have a look at this formula, right? So then, if you have too little force, right? So this is too small, right? Then what can you do without changing the force to change the total torque, right? Of course, you can make L bigger, right? Then that is the answer. You can just use you can just have basically more torque by using a wider grip, or a different tool, right? So that would actually be two ideas how to increase your torque. And so that's what torque really is, right? Torque is just a force. Your hand is turning the thing, it's turning it, right? And the distance, right, from the force to the center, right? So, and by actually, when you have a torque, you always have to define a middle, or a point of reference at least, right? So you always have to define where our point of reference is. So when we actually write that the sum of all moments around a point where, well, let's say, what if I choose my point to be exactly in this point right here, right? I'm just gonna write A right here. So what happens if I choose that, right? A is equal to 0 is equal to, well, let's think about this for a second. First, also, one more thing to do is in mathematical sense, right? So you have math, you have clockwise is negative, and counterclockwise is positive. Just keep that in mind, okay? So this kind of turn equals a positive sign before the variable, and this one equals a negative one, right? So basically, when we have positive, we don't need to write it unless it's not the first term, right? Anyways, so let's actually continue. So if we were to write down this, we said that a moment is just force times the length of it, right? So let's actually do this, right? Okay, so we have F, which is just pointing down, right? But we have our point. Let's just say that I have my my tool is here, right? And I'm trying to turn around this point. Right? Which way am I turning? Am I turning positive or negative? Well, I'm turning positive because I'm going against the clock, right? So this has to be a plus, right? This is just for you guys to remember that, maybe, you know. So it's a little bit easier, right? You don't need to write plus here because it's, as I've said before, it's not really necessary. But anyways, let's for practice just put a plus here, right? So you have plus F and plus F. And the question is which F times, because F times, which distance do we have to the point? Well, that's of course just the length over 2, right? Length over 2, right? Great. And now we have another force, this one, right? Or first, let's have a look at this one actually, right? Now let's just have a look at this one. So we have plus or minus, what? That's pointing directly towards our point. What does that tell us? Well, that tells us exactly one thing. It has no torque. There's no torque that is being applied from this force to this point. Why? Because it's pointing directly towards the point. It could also be pointing the other way, or any way, or this, or a force like this also has no torque if it's pointing directly towards the point. Alright, so keep that in mind, guys. If there is no distance between the point of turning and our force, there is no torque. Cannot be, because if F is some value and L is 0, we get value times 0 must be equal to 0, right? So we just have 0. So we just leave that out, right? So yeah. So now continuing on, let's maybe look. I don't know where my pen is again. I'll just use this one anyway. So we have plus F over plus F times L over 2, and then the last force that we have not considered yet is this one, right? So we have F over 2, but it's not the same, right? It's a different one. So we have to also write torque for that force, right? So let's have a look. What is this force doing, right? So we can see L, we can see F over 2. The question is, turning around this point, which direction are we turning towards, right? And we're turning in the positive, in the positive clockwise direction, which means it is actually a negative F over 2 times the whole length, right? Because we have the whole length as our distance. Yeah, that is actually already the solution for this. Now, I have not plugged in any numbers yet because this was just the basic understanding. And this was a very simple example of forces and torques. But what happens if we, for example, have this force, right? What happens when a force acts at an angle of, for example, alpha, right? What happens? Well, let me actually cover that, and that's going to be quite it with this video. That's just a quick one, right? So we're going to have F here, and then we're going to have Fy here, and then we're going to have Fx here. Now, why does this work, right? So basically, to understand this, you have to think about the fact we can split every force into its components, right? So there's a right angle here. So what you guys might already see is that F squared is Fy squared plus Fx squared, right? So this is also a kind of formula that we have for the forces. And of course you can find the angle alpha in here, right? So this is how this works, right? So when we have a force that is not exactly pointing up or down, we actually have to consider the y part and the x part. Now, the y part can be taken up by, of course, by, you sit on the bench. It has a specific load that it can handle before it collapses. But this x part would mean that you're not only sitting on the bench, but you're also pushing the bench. If this were the bench right here, if this were the bench and you sat on it, you would also be pushing the bench in one direction, right? So you would be pushing the bench, in this case, in this direction, right? This is the direction of pushing. So, of course, the bench has to have an equally large force that is pointed towards the opposite direction to compensate for that, right? Because if it didn't have that, it would start moving. It would start moving by the force F, right? Which is, of course, again, then F is m times a, but let's just forget about that. So this is just a very quick introduction into this topic. And maybe one more thing to give you guys before I end this video, right, is so you have sum of fy, then you have sum of fx, right, is 0, and then you have sum of m is 0. One last thing, we have torques, right, m. And there is one thing that is specifically handy in cars. There's the big letter that is P. This is physics, right? This is just physics. And you have P. P stands for performance, and you have it in watt, right? This is the unit, watt. And the unit of watt is joule over a second, right? So basically, the performance is the rate of doing work, right? How much work can you do in a specific amount of time? And maybe you guys can think of something in which we can actually put the m or the f in some kind of formula that we can actually calculate this. So I'm gonna actually solve this for you guys. So P is m times omega is one formula, and then we also have P is F times V in one formula. I'll not get into detail, I will just maybe write down the units, right? Watt is equal to Newton times meters per second. And then you have here is Newton meters times 1 over second. And also right here, I'm going to write omega is 2 pi f. And that's it, guys. I'm going to leave you with this. It's kind of an open end, but in the next one we're going to dive into this, right? So let's recap really quickly. Forces are vectors which are pointing in a direction and have a set length, right? We said that it doesn't matter if you pull or push as long as it's on the same line. And we have the three axioms of or actually it's one axiom of mechanics here, which is sum of all y forces, sum of all x forces, and sum of all moments must be 0, otherwise something is moving, right? And we have F is m times a, Newton's one of Newton's axioms. Newton is the unit after him, and we have m is F times L. Good, guys. Thank you very much for watching first episode on physics. Next we're gonna dive into some examples and maybe also something to practice. Thank you guys for watching, and I'll see you in the next one.